Hello. So this is going to be sort of a mini week 6 recitation video if you couldn't show up in person this week. So what I'm going to cover are basically the two things that the two types of problems we covered in the recitations. So these two problems actually correspond to problems number 4 and 9 on homework 6, and the first problem is out of section 3.1, the second out of 3.2. So in 3.1, you learn how to solve second order linear equations with constant coefficients that look like this. So we know how to solve this type of equation using factoring and sort of using that trick that if we look at the exponential function, so e to the r times x, that it possesses some nice properties when differentiating that makes it a solution to this type of equation. So a second order Euler equation almost looks like this, but it's got a few more x terms thrown in there. But for this type of an equation, what we're going to do is we're going to make a substitution. Namely, we're going to let v equal the natural log of x. And our goal is to make this substitution in order to transform this into a second order equation with constant coefficients. So if I make this substitution, I know that dv dx is equal to 1 over x. And now what I want to do is I want to solve for y prime and y double prime in terms of v and x. Specifically, I want to transform this into now an equation involving y and v instead of y and x. So I can immediately use this. So I know that dy dx is equal to dy dv times dv dx, which is equal to dy dv times 1 over x. And now using similar techniques for second derivatives, I know that y double prime, so we know this is equal to the second derivative of y with respect to v times dv dx squared plus dy dv times second derivative of v with respect to x. So this we know. dv dx we know is 1 over x, so this is 1 over x squared. If I take the derivative again, I would get negative 1 over x squared. And so I know that y double prime is equal to the second derivative of y with respect to v times 1 over x squared minus the first derivative of y with respect to v times 1 over x squared. All right, so what we can now do is take this equation that we've solved for y prime, take this equation that we've solved for y double prime, and plug them into this formula here. Specifically, what I'm going to do is I'm going to actually simplify this a little more and factor out the 1 over x squared. Because notice now, when I plug this in for y double prime, the x squared and 1 over x squared will cancel. And so I get that a times, so this cancels with this, the second derivative of y with respect to v minus dy dv plus, now notice here, when I plug in y prime for this y prime, the 1 over x and x cancel. That would be plus b times dy dv plus c times y is equal to 0. And now I can just combine like terms to get a new differential equation which we can solve, which has constant coefficients. And so what you do using sort of these two relations and this substitution, you transform this problem into one we know how to solve. And then remember, once you've gotten to this step, all you have to do at the end is just remember to then, well, once you've gotten to this step, you can solve this. After solving, you just have to remember to sub v equals ln x back in order to get a solution in terms of x and y. So I want to go over one problem using this technique. And so we want to find the general solution for the equation 25x squared y double prime plus 70x y prime minus 10y is equal to 0. So first off, we can check this is a second order Euler equation. It fits the form, so 25 would correspond to a, b, c, x squared y double prime, x y prime. So we'll let v equal ln x. We've already shown sort of the next few steps, so we don't have to go through the whole substitution process again. So we can just say then, dot, dot, dot. We know that 25 times second derivative of y with respect to v plus b minus a, so 70 minus 25, so that'd be 45, times dy dv minus 10y equals 0. So now this is just a second order equation with constant coefficients. So to solve this, use the auxiliary equation, 25r squared plus 45r minus 10 is equal to 0. Equivalent to just divide through by 5 here. And then when you factor this, you should get r plus 2 times 5r minus 1 equals 0. And so that means we've got two roots. R1 is equal to -2. R2 is equal to 1/5. And so that means a general solution to this equation would be y is equal to c1 e to the -2v plus c2 e to the 1/5 v. But remember, we're not looking for a general solution to this equation. We're looking for a general solution to this equation. So we just need to substitute in ln x for v. And actually doing so, you could then do a little bit of simplification, right? Because we put an ln x here. you get negative 2 times ln x. You could bring the negative 2 up. Then the e and the ln would cancel out. And so you'd get this as your general solution. Oh, sorry. There shouldn't be an ln there. C2 times x to the 1/5. And so remember, since it's a linear second order equation, we should be able to find two linearly independent solutions. And so this is just the sum of both of these solutions, in that any linear combination of this individual solution and this individual solution will actually give you another solution. So that is the first type of problem. And so again, this corresponds to problem number 4 on your homework. You should have a somewhat similar problem that you can work through kind of in a similar way. The next problem deals with sort of another scenario where maybe now now we have a slightly more general type of equation. So we've again got a second order linear equation that we want to solve. But let's suppose we've got this equation, right? And so here, p of x and q of x specifically, they could be functions of x that are non-constant. So constant, we know how to do that. But let's say these are non-constant. But let's say we already have one solution to this equation. So let's suppose we already know that some function y1 of x is a solution. So we want to then find the second solution to this equation. Remember, linear second order, we know it has two solutions that are linearly independent. We know one of them already. Don't know what it is. Well, we know what it is, but in general, this is just some function that is a solution to this equation. So we'll let y2 be the second solution. And so what this means is that y2 of x is equal to v of x times y1 of x, where, I'll explain what I mean here, v of x is specifically non-constant. So why is this? Well, since y2 and y1 are two solutions, and I'm here assuming that they are independent, or linearly independent, that this is the second sort of linearly independent solution from y1, that, given any two functions, I can always find some function that, multiplies the two functions. Like, there exists some v of x such that y2 of x is equal to v times y1. But because they're not linearly independent, we know that this is not constant, that this contains x terms in it, so to speak. And so our goal is to actually, instead of solving for y2 directly, given that we know y1, we want to solve for v, which will then tell us what y2 is. So how can we do that? Well, if we differentiate this equation here, so by the product rule, the first derivative would be v prime y1 plus v y1 prime. Now do the second derivative. And so this is just more product rules, but we get to do twice as many. But it's okay, the product rule is fun. You get that that's equal to y2 prime, or y2 double prime, sorry. So we've now got these two relations again, and this might kind of start to seem a little similar to what we did with our substitution in the last one, is we got this sort of relation where here again we're assuming y2 and y1 are both solutions to this. We've taken a bunch of derivatives, so we've got y2 prime and y2 double prime. And now what we're going to do, remember, y2 is a solution to this, so I should be able to plug y2 in to this function and have this function satisfied. But I'm not going to plug in maybe y2 prime, y2 double prime. I'm going to plug in the right-hand side of all of these equations. So I know that v double prime times y1 plus 2v prime y1 prime plus v y1 double prime plus v prime y1 plus v y1 prime times p plus y1 times v times q is equal to 0. And so notice what I did here is I took each of the three relations I got for y2, y2 prime, and y2 double prime, and I plugged them into this formula, which I know must be satisfied. So there's a lot of algebra that would happen here. I'm going to leave some of that because algebra is so much fun, and I wouldn't want to, I wouldn't want to do all of the algebra myself. What I will say is that I'm going to group all of the terms together based on the v's. So I'm going to group all of the v double prime terms together, the v prime terms together, and the v terms together. Doing that, you get that the following equation must be satisfied. All right. Here, we've got this function v times this long string here. This long string looks awfully familiar. Well, notice y1 is a solution also to this original differential equation. And this is the exact equation that we've got here. So this whole chunk of the equation here is actually just equal to 0. So that means we've got now a differential equation in terms of v double prime and v prime that, in fact, as we'll see when we look at an example of this, is separable. And we can solve this not for v, but we can solve this equation for v prime. And we'll get it in terms of x. And it doesn't look like it, but remember this function y1 is some known solution. So when we know this solution, all of these terms will actually be in terms of x. This will be, v differentiated with respect to x. And so we'll be able to solve this to get this nice, basically, relation where we've got v prime equal to some function of x, and then we can just integrate to get the final solution. Give me 1 second. My computer is running low on battery. All right, what did I miss? All right, anyways. So we've got that. So yeah, once we sort of make this substitution, get this equation, find v prime, integrate, find v, that allows us to find y2. Probably easier to see on an example, but I always like looking at like why does this kind of substitution work, and this is the somewhat involved algebra behind why it works. And so this is also on the worksheet for reference, so you can certainly reference all of this. All right, so this should look a lot like question 9 on your homework. And so this is called reduction of order. So we want to find the second solution to this differential equation. Given that one solution is this, and we're working with x greater than 0. So here we know that one solution to this is the equation x to the 4th. We want to find the second solution. So remember, we can let y2 equal vx times y1, which would be x to the 4th. And so as we saw, well, before we do that, and I almost made this mistake again, this is not quite in the correct form that it needs to be in order to apply this method. I made this mistake. First, we need to put it in the correct form. I made this mistake while I was originally working out this problem. We want to divide through by x squared, and that gets us the differential equation y double prime plus 3 over x y prime minus 24 over x squared y is equal to 0. And so matching all of this up with the general form, this 3 over x would be p of x, this would be q of x. So now we can solve y1 v double prime plus two y1 prime plus p y1 v prime is equal to 0. So now we just got to carefully plug everything into this. And you can see once we've kind of set up this substitution, it's sometimes actually not horrible to work through it. So this would be 2 y1 prime is equal to 4x cubed plus p, which is 3 over x, times y1, which is x to the 4th, 0. And so doing that, you should get the equation plus 8 plus 3. You should get that equation. So this is separable, and again, we can solve it for v prime. I hate looking at primes, so I'm just going to quickly let u equal v prime, then du dx is equal to v double prime. And so it's equivalent to solve this equation, which this is separable. You get the du over u move this over to the other side, divide by x to the fourth is equal to negative, sorry, this should be 11, not 8. 8 plus 3 is 11. Negative 11 over x dx. And so now we can start solving. So to save a little bit of room, maybe I will kind of start working my way back up here. So maybe we'll erase these two things. Oh. And then do that. So solving this differential equation, we get ln u is equal to negative 11 ln x. So this implies that u is equal to x to the negative 11. Remember, though, u was equal to v prime, which is x to the negative 11. And so v would be negative 1/10 x to the negative 10. So remember, this is the function v such that our second solution was equal to this v times that times that. And so you could write this times x to the negative 6 for y2. So remember, this was the function v that we were solving for here that gave us the second solution. So here I'm just plugging this in. We can actually make it a little more general than this and just write y2 equals 1 over x to the 6th as a general solution. The reason being is actually any constant multiple of this will also be a solution. If you think about sort of taking the derivative of this each time, we could actually just always factor that constant out. And so we can just drop the negative 10 to make our lives a little easier. So yeah, so that would be kind of how you would apply this process to sort of this reduction of order technique, where you've already got one solution and you want to find the other. Yeah, so those were really the two problems that we wanted to cover this week. So certainly if you have any questions, there are a couple more practice problems on there that we didn't get to in the recitations. If you want to talk about those, I'm certainly happy to if you email me, or I'm certainly happy to talk about some of the other problems that were on there. I'd also, if we had gotten time, included a review of different review of what's the word? Determinants. Yeah, differentiation determinants. We didn't end up getting to cover that in recitation because we mostly talked about these problems. I'm also happy to talk, if you want to discuss any of those problems on the end of that, I'm more than happy to talk about those. So yeah, thanks for watching.